Then, good morning, everybody. So first of all, I would like to say sorry that we do not participate for this event. It was, according to Corona rules, we had to reject the personal to be present in person. However, as you can see, we listen to the online part. So first of all, I would like to thank the people who organized it, especially for Thomas and Fumia and also Bram, to give me the possibility to show a little bit the overview about the sensor development and sensor integration, which has been done mostly by the Zero project at the moment. So in the Smart project, what I saw, there are not so much things done, and they are more focused. The things what I saw are more focused on the robotic part. So I think this is then something which will be given an overview by Thomas and by Sepe on Thursday. So let me start with my presentation. So first of all, what I would like to show you is the development of self-healing sensors and also the development of characterization of sensor types, which we investigated during the Zero project as well as on the Smart project. And here I tried to bring all the different sensor papers inside, which has been already published and which are available for the people who are listening to this talk. So first of all, let me say what is the intention for us. So the intention for us is that we have kind of senses which we can do or which we can mimic, so that we have these biomimetic sensors where we can integrate sensors for visual, for audio, for gesture, smelling, touch, and other kind of sensings probabilities which we normally have in our body. And by this, it's clear that when we want to develop new sensor systems, we have to think about that we want to do multi-sensing, as it was already discussed this morning, that we want to have selectivity, so that we need sensors which only sense one of the signals and not the others. And then for sure, we need flexible and self-healing sensor materials. So in the project, we started with the development of conductive polymer composites, and this is mainly what has been already done in the whole project, so that we are looking on polymers or on self-healing materials, elastomers and thermoplastic elastomers, and we put inorganic particles inside, and by the percolation curve, which you can see here now nicely, you can change the conductivity depending on the amount of conductive filler you put inside. However, if you look on this structure a little bit more intensively, you can see that we have different phenomena. So you see here that either we can have the conductivity by the electron transfer through the chain of the particles which are generated above the so-called percolation threshold, or we have a distance or larger distance where we then talk here about tunneling effect or here about hopping. And the main difference, if you think about hopping of the electron from one conductive particle to another one, or if we have this tunneling effect, is the energy level, which you can see underneath here. So that means if we have a hopping effect, the electron has to have so much energy, kinetic energy, that it really can jump from one to the other conductive particle. In the conductive, so in the tunneling effect, the distance is normally smaller, and by this, the idea is that when we have these wavy function, Then if we have a kind of barrier here, which is not conductive, then even due to the high energy which the ions, the electrons still have, it can move to the other particle, and by this generates an electrical conductivity, even though that the particles are not completely together. So when we look for the percolation curves, you can see here nicely that depending on the different materials which we can have either low percolation threshold or low percolation point here, or high percolation point and high percolation thresholds. And you see that, for example, when you work with carbon fibers, you see that the percolation threshold is quite high. So you see it's about 40%, which you need to be conductive. And if you use carbon black, these values are much lower. And if we go to carbon nanotubes or graphene, you can even go below 1 volume percent. So the interesting with carbon nanomaterial-based conductive polymer composite sensors is that you can use the same material for different kind of sensors. So that means we can either use mechanical sensors, which is a strain, pressure, or tactile sensor, as it was already shown before, and that we can achieve by a piezoelectric or by a capacity effect, or we can use a thermal temperature sensor, which means then we use a thermal expansion of the polymer to drive the sensor, or we can use the heating element. So we can also make a heating element by applying a high voltage and so allow a certain current to pass the material. And then we can also use here the thermal expansion of the polymer matrix to adjust the temperature which we want to achieve by applying a certain voltage and a certain current. And the other thing is what we can do is we can also look on chemical sensors, which is then a swelling of the polymer. And by this, we also get a larger difference, or the particles will go not closer together, though they will go away from each other when we have the swelling effect. So the particles distance will get larger, as well as we have for the heating effect, but due to the swelling. And another point is then you can also make these acoustic sensors. So already in the 20s of the last century, for example, they made microphones based on these conductive composite materials based on carbon. So how did we now look inside these materials when we worked in the Shero and in the SMART consortium? So here you see, for example, a paper which was published in the beginning of the Shero project, where we started to look a little bit closer inside piezo-resistive sensors, so based on carbon materials. And here you can see, for example, typically what the people are looking for. So either the people are using this kind of cycling testing, as it's shown in the presentation before. And this is pretty good to show a little bit the reliability of the sensor, and also to investigate the so-called gauge factor. So which gives you more or less the sensitivity of your sensor. That means it tells you how much the resistance change from the initial resistance, so where you had no strain on it, up to a certain strain which you apply to the sensor. And then typically what you can see in the literature is that the people have a kind of drift, so that the first, second, third, fourth, and fifth, and so on cycle do not always, you cannot always achieve the same resistance at the same strain. However, if we want to have a very good sensor, so you can imagine that this drift must be very small or even neglected. And another possibility to measure sensor properties or sensors, and to see if you have a good sensor or a bad sensor. You also can use these quasi-static experiments or quasi-static tests, where you have again a cycling process, but in between each cycle, on the top and on the bottom of the strain, you always keep a certain time where you keep a constant strain on the material. And therefore, what you can get out is, for example, you can get out the so-called relaxation effect. So that means how much your resistivity or your conductivity changes by time. So in this case, here is the resistivity or the resistance, how much your resistance drops down. And this gives you a little bit the feeling how reliable or how accurate your sensor is. So can you really use your sensor to really detect very nicely different strains? Unfortunately, if you look in the literature, as I already mentioned, very often the people look on this kind of hysteresis. They look a lot of dynamic experiments for the reproducibility, to measure the gauge factor. This is what you see in 99% of all the papers. But the quasi-static tests are very heavily ignored in many of the publications, even though if the people will do this, they will see that their sensor maybe will be not as good as they propose. So according to this literature research, we started then to develop our own sensors. And you can see here, further develop our first sensor, and you can see here two kind of sensors. So this is a sensor which we develop by ourselves. This is a sensor which you can buy on the market, or the material through it. And here what we did is we did by fused deposition modeling, by 3D printing, we extruded or we printed both of these materials, and you can really nicely see here in the graphic what is the problem. So if you have this commercial sensor material, then you can see that this is almost impossible to measure anything at low strain. So you see, if we go here up to 70% strain, you can see here that we have a secondary phase, a peak. And this secondary peak which we have tells you that your sensor is not accurate to measure really at small strain levels. However, you could say, okay, look, I use different technologies to know exactly what is the slope, and by this I read out my sensor. But if you do then this quasi-static cycle experiment, which sometimes happens, so you move, for example, your robot, and then you stay at a certain position, and you see that you can almost not neglect anymore or select anymore in which state you are, because it's just these peaks which you can see very nicely when you change the strain inside your material. And this is, for example, due to the change of the charge density in the material. And here, for example, you can see a sensor which we developed by ourselves, and you can see that nicely we can follow the strain signal, as well as you can see that even when we apply this quasi-static experiment, we can get a very good and stable sensor signal. So the other thing was then that we wanted to know, okay, what's happening if we put that now into the matrix? Because this is at the end the idea. The idea is clearly that we put the fibers into self-healing matrix systems. Why do we want to do this? Quite simple. If we fill the whole material with conductive material, we have two disadvantages. The first disadvantage is that we reduce the self-healing process or probability, and the second problem we have is that we stiffen the material. And what we want to investigate are soft materials. According to that, we follow the sensor fiber approach. You can see here the fiber, and if we use it now in a PDMS, which is typically used by the robotic people, you see that we get here a small increase in the sensing behavior. So that means we start here to get a secondary peak, as I showed you before, but not as strong as for this TPU material, which is commercial available. However, what we could see then, if we put a spring inside, which gives me clearly an elastic behavior, or if we work with natural rubber, we can completely neglect this secondary peak when we pre-vulcanize this natural rubber. And what did we, when we looked a little bit closer in these mechanical properties, we saw that we could make two classes. One class was with materials which has a high stiffness, these matrix materials, and the other one, they had a low stiffness. And you can see that for the high stiffness materials, we get good sensing behaviors, and for the bad one, for the low one, we have the secondary peak, or we have here a plateau, which also does not give us the possibility to measure low strain. So according to these results, we thought about, okay, the sensor is always the same, but what we see is that the matrix affects these sensor properties of the sensor quite strongly. So therefore, we thought, okay, let us make an experiment and let us see what's happening if we use two different silicone materials. So here is again a PDMS material, here is an Ecoflex material, and the structure is the same. So this is, we did the sensor composites by simply casting. And the interesting part, what we see is that you can see here the fiber, and the fiber has really the highest resistivity when we have the highest strain. And when we put the silicone material, you can see, as I already mentioned, the secondary peak. Interestingly, if we use this Ecoflex material, we have a completely reverse behavior. So you see that the fiber, which is still the same fiber, tends to have completely different sensor behavior. That means now instead of the maximum resistivity, we get the minimum resistivity at the highest strain. And then we did some mechanical analysis, and we tried to do some composite analysis, and we could see that when we apply this, or when we have a lower stiffness of the matrix, what we could see is that we cannot calculate anymore the strain stress behavior of a fiber. That means the fibers is somehow decoupled from the matrix, or in other words, we have a strain shielding of the matrix, and that means that the fiber will not see the strain which we apply to the matrix. We first thought, okay, this is a bad behavior, so we have to avoid it. However, by Thomas, he found then a way that he said, wait a minute, we can use these bad materials to build up a system where we have then different kind of sensors. So you see here sensor 1 and sensor 2. And then by the different behaviors of the sensor 1 and sensor 2, we can neglect the drift and the relaxation, and we can, by using a neural network approach, we can then read out the right sensor data which we need for the application. While Cambridge was looking on that, we still tried to investigate and analysis again for the other people who are working with us in this field, how it must be the self-healing matrix look like, so that they are good in a good comparable way with our sensor, or with the new sensors which have been also to develop by self-healing materials. You can see here again, we did now a more systematic study where we worked with two different shore hardnesses of the fiber and three different shore hardnesses of the matrix. And the first thing what we saw is that when the fiber is too stiff, then the matrix will really completely stress shield the fiber, and according to that, you cannot read very useful sensor data out of it. But if you reduce the stiffness of the fiber, so this was then a new fiber which we developed based on the old one, and by this, for example, you can see that we can even go to much lower shore hardnesses of a silicone matrix, and we have a very nice comparison, or there is a good match between the model prediction and the tensile test which we did on fibers. So according to that, here now the composite model is working, and according to that, we also got good sensing behavior out of it. So in other words, as main conclusion was, low fiber shore hardness must be combined with low matrix shore hardness. So you really have to look on those materials. Then we started to do the 3D printing of these composites, so where we tried to integrate these fiber materials by 3D printing inside a 3D printed structure. Herefore, we used, first of all, the TPU material, which is commercially available. And what we also found here again is the same thing. So when we had a higher shore hardness of the matrix, we get a better response from the sensor. So the same as we already saw before. However, I would say with the TPU, and I think this you could also nicely see from the presentation before when we looked on the Mooney effect, which was shown in one of the slides, you see that these materials has a little bit of problem because TPU likes to have a large viscous behavior, also the viscoelastic behavior. The viscous behavior is quite high for this material, and the relaxation is quite bad for these materials. Then after a while, we found then a way to also process soft materials, and this is what you can see here. And by what we did is we used a pellet extruder, and with the pellet extruder, we could then nicely produce very soft materials. These properties were similar or are similar to normal silicone, so we can come up to a shore hardness below 20A, which is in the range of eco or the Stragan skin, which normally is used. Later on, we looked then a little bit, so what's happening if we work with self-healing materials? So here you can see a self-healing fiber integrated in a self-healing matrix. This was done together with Suprapolix and University of Brussels. And you can see here nicely that what we found out is that when you work on this kind of pneumatic actuator, where when we apply here a pressure, then the sensor will be working under compression. Here the sensor will work under strain, and we can see that this composite, which has been developed together with Suprapolix, there we see that the strain behavior is much better than the compression behavior. So compression is almost not really detectable by the material if we have a damage inside the matrix. Later on, we thought then, okay, can we go a little bit further on this? Can we look a little bit more on the damaging and the healing mechanism according to the pneumatic system, which we already saw? And to have it a little bit better controlled, we decided to use these tendon-based bending actuators. And here you can see nicely that with the self-healing material, for example, if you see here the damage and the precedent, so that means before damage and after healing, we can achieve almost the same behavior, the sensor behavior. However, the damage, for example, is clearly different to it. And by this, we now have a really good sensor to detect, on the one hand, the damage, and on the other hand, the healing of the material. Another approach which we did is then when we put this inside, these were tensile experiments, and now we did the bending experiment. And when we do the bending experiments, unfortunately, here we do not get this perfect results out from the tensile tests, and you can see that still the relative resistance changes continuously, and you can see that we have always an increase in the relative resistance between before damage, and healing. last but not least, this is now some papers which are under submission at the moment. This is a paper made by the people from France. And here you can nicely see a sensor behavior, which was, or sensor, which was integrated in an epoxy vitromer material. And by this, you can see that when the fiber was not very well attached to the matrix, we had a delamination. However, by using some additives, it was possible to have a better adhesion between the fiber and the matrix material. And by this, we could get a very good sensor signals out of it. Nevertheless, you can see that still there must be some improvement, because you see that we have here a high drift of the sensor behavior according to the cycle number. To show that even the self-healing properties are possible by even using a simple TPE material, so by using a thermoplastic elastomer, which without any hydrogen bonds, we started to develop these self-heating or self-regulating heating elements, which we integrated in our matrix material. And then what we did is we heated the material up, and this you can achieve by applying either different voltages or by making a cutoff of the current which is possible to achieve. And by this, you can then adjust a certain temperature which you need. We did that, and we placed the temperature close to the melting temperature of the TPU matrix material which we had. We made a cut inside, so this is what you can see here. And then by heating up the elements, you can see that we could close this cut here, and we could self-heal the TPE material. By this, I would like to conclude, and I think you can read it by yourself. I will shortly say that percolation theory is important to evaluate and develop conductive materials, conductive polymers. You will see also this afternoon some more examples by Antonia when she gave her tutorial. And you can also see that the golden standard for analysis of conductive polymer composites is still not existing. I think this must be really fastly improved, because otherwise we have a lot of papers with no meaning, because we really need to understand better how the behavior, the sensor behavior is, and we need to be able to compare the different sensors, which is almost impossible because everybody works with different strains. And yeah, so therefore this must be really improved from my point of view. I would say we also could see that self-healing materials with integrated self-healing sensors, we already could achieve successfully. And by this, I think we can really show in the end of the project the device prototype which we should do. And finally, using carbon filler heating elements can be fabricated to achieve even self-healing in conventional TPE materials. I think this is also giving a very good prognosis to also use other materials instead of only self-healing materials in the future for soft robotic applications, and use the self-healing mechanism. By this, I would like to thank you for your attention, and I would like to thank all the partners from the SMART and from the SHIRO project, as well as I would like to thank the EU for supporting us for these two projects, SHIRO and SMART. Thank you very much. I think I will hand over to Joost, and we can
I think we can take a quick question while Joost is setting up. And we have some questions in the chat.
We have some chats, good. Just a second. Okay. Yeah, there is one question. How did you measure capacitance method of strain sensors during loading and unloading cycles? I did not measure the capacity. I did even not show any capacity method, but this is quite simple. So what will happen when you have a capacitor and you strain the material? That means you change the distance between the two electrodes, and by this you change the capacity. And by changing the capacity, you can investigate the strain. Good. I think that was all from my side. There are no other questions online. And I see that Joost is ready to give his presentation.
Yeah, I can't show you. So yeah,